The predictive power of traced. Hey guys, I'm Brian Osborne. I'm back with Dr. Nathaniel Jeanson, and we are talking about his book, Traced. This is video number 14, actually, if you're keeping count. Gone through a whole lot of information we've been looking at recently, really how Traced sets a gold standard for science, or is part of that gold standard. It really does meet that qualification and does excellent, has excellent predictive power. And we'll see more of that today in this particular session. We covered a lot of information, but there's still a lot more to go. And it's going to be so helpful in us understanding really this new Rosetta Stone of human history, connecting the dots for us as Christians in the biblical worldview with some good science to humanity. And so I'm excited for today's session. I'll turn it over to Dr. Nathaniel Jeanson.
Thank you so much, Brian. And today's session is going to be a little bit more of a review of sorts, I'd say. Not because it's all going to be stuff we've heard before, but because I get to give a big finish to a story I've been building. And so if you're binge watching this and you're saying, well, how come you're reviewing what I just saw? Because it's an integral part of building my case. So let me just back up and again, put it in the bigger picture. Then I'll get to this review. And then by the end of this, we're going to shift gears. I said I wanted to give you a chronology of what's going on in this research, the science behind Traced. And again, this is part 14. So if you're joining this fresh, there is some key information in the previous episodes that I invite you to see, and it's the integral part of this case that I'm building to say this is how we know it's true. But this is where we get to finish this little subsection that I've called the Y chromosome element. The main tool, genetic tool that I'm using in this new book, Traced Human DNA's Big Surprise, to uncover human history is the male inherited DNA, the Y chromosome. And I'll be able to finish this little section of history for that. And then by the end of this little lecture, we'll shift gears and go back to the beginning stages of the research, over a decade's worth of research that led up to this. It didn't start with the Y chromosome, and this adds, I think, to the independent lines of evidence that confirm what's going on here. Again, part of the reason we're talking about this is because this book is based on a young Earth creation framework, which is, in today's culture, viewed as pseudoscientific at best. I've said the opposite and said that this book represents one of the strongest arguments in print in support of the recent origin of humanity. So, of course, that raises the question, how do we know this is true? If this disagrees with what so much of mainstream science articulates, why would anyone put confidence in this? And the standard we've been seeking to meet, the gold standard, which Brian referenced just a few minutes ago, is this one that's been consistent for decades in terms of being articulated by my opponents against creation science. It's also long been part of the scientific process. This isn't just some invention of the evolutionary community to try to make life difficult for creationists. This just flows from the basic nature of how science works as a method of knowing the world. So again, the quote from a popular evolutionary textbook, the most important feature of scientific hypotheses is that they are testable. So does creation science make testable predictions? Does the research in this book make testable predictions? The point that I've made several times over and over again, and I'm going to make again because it's so foundational to what's going on, my answer to how do we know that this research is true? It's because it's part of a historical progression of discoveries in which successive, testable, young Earth creation predictions keep working. And so I want to review for you, not the entire decade. We'll hopefully do that next session in short order. We've been laying it out in chunks over these few sessions. What I want you to see is that there's several years worth now of Y chromosome research in which this more predictions, fulfillments pattern has been going on. And this underscores the veracity of the conclusions. So once again, just to emphasize, so we're all on the same page, this family tree based on the male inherited DNA is the central focus of Traced. What we're calling the new Rosetta Stone of human history is a generation by generation family tree for global humanity based on this male inherited DNA. How did we get to the point where in this book I could begin to read off the history of humanity from the branches on this family tree? We talked about some of the early experiments that were done. Again, the Y chromosome is passed directly from fathers to sons. Females do not have it. It's only a fraction of the male's total DNA. We know that over time, as the father's sperm cells copy the Y chromosome, pass it on, and it ends up in the son, there's mistakes that occur. And of course, one of the big questions is, how fast or slow does this error process, these copying errors occur? These mutations is the term. we talked about the history that led up to this. Some of the early studies that were based on low-quality DNA, low coverage was the technical term, and you can see the previous episodes for the explanation of what coverage corresponds to. And by 2017, I was aware of 4 published studies. 2 were of low quality, low coverage, 2 are of high quality, high coverage. The high quality DNA sequences pointed towards an origin for humanity just a few thousand years ago. In other words, the rate at which mutations occurred seemed to be fast. If it was slow, it might argue for an ancient origin for the paternal line of men all around the globe. Instead, it ticked, this clock seemed to tick quickly. In these high coverage, high quality sequences, this was exactly in line with the expectations already published in the mainstream literature based on the technology of DNA sequencing. So far, so good. Things are working as expected based on purely technological considerations. From a mainstream evolutionary perspective, big problems. We can't have the mutation rate being too fast. The evolutionary community responded by literally filtering out data. And we talked about how these low coverage, low quality studies, 2009 based on 2 Chinese, 2015 based on some Icelandic pedigrees, gave mutation rates in line with evolution, high coverage in line with creation. These numbers that may not seem like much right here translate to something meaningful like 3 mutations, 3 mistakes per generation. This can explain the differences that we see around the globe in just 4,500 years. So long story short, this initial line of evidence that I wrote up in 2019, you can see the other lectures we've done, the webinars we've done for the specific references. That table I just gave you came from a 2019 paper that looked at these father-son mutation rates. One of the objections that the community could raise and has raised is, hold on, you're using the DNA just from living men. You're not including ancient DNA, like DNA from Neanderthals. That objection would change some of the conclusions that I would have made. I said this mutation rate between fathers and sons was fast, too fast. There would be too many mutations for evolution to try to stretch out human history over hundreds of thousands of years. They would predict all sorts of mutations after hundreds of thousands of years. We see very few. If you add an ancient DNA, this bar would go up and would seem to bring the results in alignment with evolution. I said this fast rate of father-son mutation rates captures a lot of these dark gray, black bars that we see right here. I'll talk about this larger bar here in a moment. But if you add an ancient DNA, you have even more differences to explain, seemingly too many differences to explain in a time frame of just 4,500 years. The other objection that I just alluded to that the community has raised, and a fair question, is how do we know that the 3 mutations per generation, if we accept it as valid, has been a consistent rate throughout all of human history? What if it had slowed down? What if natural selection had removed some of these mutations so that effectively it's not 3 mutations per generation, but something slower? Well, I've tested both of these hypotheses, predictions. These hypotheses make predictions. Looking at a test data set. In this case, we know from historical records, from archaeology, independent of genetics, what the shape of human population growth has looked like. And again, I'm going through all these lines of evidence fairly quickly because it's review from previous lectures, and I want you to see a chronology here. That's the main point of what I'm showing you here, because the chronology leads to a rather explosive conclusion. So back to this specific point. These black lines represent the known population history of humanity from non-genetic sources, historical records and archaeology. The blue lines represent the reconstruction of human population history from the branches on the Y chromosome tree. This directly tests whether this mutation rate has been consistent throughout human history, because if it has, then you'd expect this match, and it's a 94% match. It's incredible. If the mutation rate had slowed down, this sort of match would go away. If we include ancient DNA, reorient the tree, do exactly what the evolutionists are asking, and incorporate them into this data set, you can reconstruct human history. It's the set of blue lines. There's actually 2 blue lines right here. It's hard to distinguish them because we're zoomed out here. But the bottom line is there's a much poorer match when you include ancient DNA. It does a much worse job of reconstructing the known history of humanity than if you just do DNA from living men. So this is the empirical reason why I've gone with the DNA just from living men, because the Y chromosomes from Neanderthals do not yield scientifically valid results. We can test it with these independent data sets. So here's a reference to that particular paper. The Y chromosome tree captured the global history of human population growth when you had a 4,500 year time frame and you use the DNA from living men. When you include DNA from the deceased, you get a very poor match. This makes additional predictions. Again, the bigger picture point here is a chronology. You start with father-son mutation rates, found a result that seemed consistent with young Earth creation. Do you stop there and just say, the end, we found what we needed, we're going to ignore everything else? No, science works by making testable predictions that predicted global reconstructions of human population history. This global match, stop here. Is the point just to fit facts to conclusions? Creationists are just looking to support the Bible, and if we find something that supports it, we just go home and call it a day. No, it's doing science. Makes more testable predictions. This predicts regional population growth curve matches. And you can see the previous lectures and also this book, because I didn't get to cover all the matches on a regional scale. There's new matches that show up in this book, Traced. Stop here? No. Step 4 then in this process. What about known historical events? And in fact, there's even more to this story than you can find in some of the published papers. If you look back and see where I've done also presentations formally at scientific meetings. This whole narrative starts about 2017 when I'm working on looking at the genetic echo of the transatlantic slave trade. Ugly history, sad story, but tremendous amount of documentation and available data from African Americans and indigenous Africans. And we got very close to publishing our results, but the question that bothered me was we've focused only on one small section of the human historical puzzle, one specific historical event. One of the main objections people might raise is, well, how do you explain the rest of the tree? Fine, you might have found some match just here in this specific subsection. What about the whole rest of the tree? It's something that I had to wrestle with for quite some time. So here, now basically 5 years later, 4.5, 5 years later, finally have an answer to this thing that has nagged at me. It also flows from these population growth curve matches. Let's drill down and say, can you actually see the echo of the history of civilization in our DNA? And the book Traced is basically a book-length answer saying, yes, it does look plausible. You can see the known events of human history pop up in a way that makes sense. Referred to a few of these in previous episodes about migrations of Central Asians into Europe in the Middle Ages and the genetic echo of that. We could talk about, and you can see, I think in episode 1 of this YouTube series, that abundant echoes, multiple independent lines of evidence pointing towards specific branches following the migrations and conquests of the Arab Muslims, and on it goes. This book looks at the entire globe and the history for the entire globe. So yes, you can see the stamp of the history of civilization there as well. Perhaps the most explosive data did not come at the beginning of this process. You might think if creationists fit facts to conclusions, they'd start by going and looking for Noah. And this is something you can verify for yourself from what I've published. I have not had a knowledge of where Noah is in this tree until late in the process. I had 2-3 papers already published on the Y chromosome in which I said, hey, Noah could be here, he could be here, based on how well it matches the known history of human population growth. Couldn't nail it down. And it wasn't until as I narrated this in a previous episode, April of 2021, when I did a deeper study of what the Bible says about what happened to the men in Genesis 10, that multiple lines of biblical evidence lined up with multiple lines of the Y chromosome tree I'd already worked out independent of a specific Noah position, historical explanations, and all this lined up. And you'll have to see chapter 13 of the book, as well as some of the discussion in previous episodes. I think if you have a subscription to answers.tv, there was an episode I did in May of 2021 when this is fresh, about an hour and a half long episode in a separate series, again, subscription based, where I talked about that. I think it has Abraham in the title, where I walk through this as well. But strongly urge you to look at chapter 13 for this book and the multiple lines of evidence about what Scripture says does happen to these men, doesn't happen to these men, where they go, where they don't go. And this just lines up extremely well, down to the level of being able to count off specific generations from Shem down to Arphaxad and other sons. Genesis 10 is a very specific genealogy. The 3 sons of Noah have different numbers of generations recorded, and those differences are even observable in the Y chromosome tree. It was that level of agreement where in April, May of 2021, I said, okay, I think we've found it now. it's risky to say this is where Noah is, because we've got 99% of today's men who have yet to take a Y chromosome test. How do we know this is going to last? And to be able to see all these lines of evidence come together is what said, you know what, I think we can confidently put this in print and say this is a legit way to go forward. We've got the echo of the Y chromosome tree, of Genesis 10 at the base of the Y chromosome tree. Again, someone might say, well, creationists fit facts to conclusions. They found their precious Noah in the tree. Time to stop and go do something else. No, this is science. This itself makes testable predictions. I alluded to one of these. I should say I explicitly mentioned one of these in a previous episode in this YouTube series. This whole model makes predictions for some of the longest branches. So in case you've just joined us for the first time and you haven't seen these previous episodes, you may have noticed in this earlier slide when I said, here's the predicted number of mutations or copying errors from a young Earth perspective, and these dashed orange lines represent the range, how this captures all but one of these right here. Well, isn't that a prediction? This is haplogroup A00 for those who want the technical term, one of the longest branches in the tree. It's not a contradiction because no one has actually measured the rate of change in these men. And one of the predictions of this model, because their branches are so long, is that they should have even faster rates of change, faster than 3 mutations per generation. That's testable. And if evolution wants to be science, if evolution wants to be considered scientific, if the mainstream community wants to have a scientific explanation for human origins, they need to be able to predict the same thing. Why would you pick this? It's not me who makes the rules. Scientists, philosophers, evolutionists have said making testable predictions is the gold standard of science. By definition, that means saying something that we have to evaluate in the future. Not something where you turn around and say, well, given the data that we have, I can make sense of this. Anyone can do that. Pseudoscientists can do that. Scientists are able to make predictions for the future where we don't know how things are going to turn out. We have to do an experiment. And if you don't do that, the evolutionists have said, philosophy has said, then you're not doing science. Now, why do I pick this? Because there aren't that many things left to test. We already have Y chromosome sequences for men around the globe. We already have father-son mutation rates for several sections of the tree. Make a prediction for what's left to be tested. This is one of the few things that's left to be tested. That's why I'm highlighting it. And if the evolutionists cannot come up with a prediction for this, by their own standards, evolution is pseudoscience. Not me saying it. I'm applying the standard that's been set for over 40 years and applying it consistently across the board. There's an even bigger aspect, though, and the whole reason I've reviewed all this is because it leads to this big finish. Where do we go from here? If creation science is science, what predictions does it make for the future? What predictions does traced make for the future, for things not yet done? And this is perhaps the biggest aspect of what I'm doing. I've got the sentence right here on the screen. I'll explain it for you carefully because there's an inherent math element that can get complicated quickly. I'll try to lay it out simply. And there's been at least a critic or two who's caught this. They think it's a criticism, but I'll give you an example of how it's already been working and why it gives me confidence that this will continue to work and why it's the basis for the research I'm doing going forward. So changes in the Y chromosome tree as more branches are added. What am I talking about? Well, it goes back to an observation that we just were looking at. And in a sense, it flows out of the match that we saw between the history of human population growth and the Y chromosome tree. So here's a graph, once again, of the history of human population growth based on archaeology and genetics, not on DNA. And it's got this hockey stick shape. This was the type of graph that I had put in print in this paper, where I said there's a 94% match. You can see these two black lines are the range of estimates there throughout the 1800s. This shows you this graph that I just had right here is the through the year 2000, basically, close to 8 billion people in the world. And I said, when you look at this Y chromosome tree or other Y chromosome trees, I had a different data set in 2019. You could again see this very tight match. This leads then to prediction. So let me back up here a second and point something out. If you look at the details of this graph, I've got a common horizontal axis where negative numbers represent years BC, positive numbers represents years AD. There's actually a year 0 I've included as part of this, even though it doesn't exist, again, because it's just easier to graph in Excel. But I have different vertical axes. In black over here is the estimate of human population history from archaeology and genetics. In blue are the number of Y chromosome lineages over time. 350 is the top of the vertical axis here. 550 million is the top of the vertical axis here. So the agreement is not in absolute numbers, at least in this paper. I'm not saying that I've got 550 million branches in the Y chromosome tree. I've got less than 350. Instead, what the match in this graph shows is a multiplicative one. The ratio between branches at this in the 1500s versus branches in the 300s BC is the same mathematical proportions as men in the 1500s as men in 300 BC. So if you were to take from the black line, let's just pick 1700 here, so you can see an estimate for 1700s is approximately 300 to 350 million people alive in the globe. And it's one of these minimum estimates. And you go back to, let's say, 1000 BC, and there's approximately 50 million men. Well, 350 divided by 50, do the math. What is that? About a 7-fold difference. You can take the number of branches here for the blue lines, 1700s. You can see here it's just over 200 branches. And you go back here to the 1000s BC, and it's probably something close to 30 or 40. Anyway, you do the math. The multiplicative relationships is what matches. Let me explain it a different way. Here's the graph of that world population growth again. From the 1400s until now, there's been a 20-fold change, multiplicative again. From the 1400s back to 1000 BC, there's only a 7-fold change. There's how much you have to multiply. Let me give you a practical example of this. And I think I've alluded to this earlier. If nothing else, it's one of the opening chapters of the book. Family trees inherently record population size. The number of branches on a family tree tells you something about changes in population size. We've looked at the example of Jacob and his 12 sons. If you were to graph out one branch from Jacob, 12 to his boys, you'd inherently have in that family tree a statement about a huge population expansion in the male line, 1 to 12. That's true for nuclear families. It's true around the globe. If you look backwards in time, from the present to 1400, there's a 20-fold change. The number of branches today is about 8 billion, close to it. The number of branches that would have existed in about 1400 would only have been 350 million. And to go from nearly 8 billion branches today back to then, you'd have to connect the branches. Why am I telling you all this? All this math leads to very specific predictions. What if I say I want to discover a new branch that originates in 500 AD? These multiplicative relationships tell me how many men I need to sample to do this. Or let me pick an easier one here to see on the graph. Let's say, just to fast forward a slide, today's family tree looks like this, with a certain number of branches. And the evolutionary community would say that the last 5,000 years represents just the very tips of this tree. I'd say the last 4,500 years represents the entire tree. The evolutionists say the very tips of this tree, again, represent the modern era. And I don't think they're expecting to find many more ancient branches. My model predicts that there's a ton of ancient branches left to discover. This is maybe the most practical thing to take away from all this, even if you didn't follow all that math. My model predicts there are a ton of additional ancient branches, ones way back here, left to be discovered. And here's how you'd find them. With this math. So 20-fold times 20 times 7. 7 times 10 is 70. 70 times 2 is 140. Let's say I want to find more branches that go back to, that originated in the 81,000s. This math tells me I would need to sample at least 140 men to have a statistical chance of finding that. that sort of relationship, the match that I just showed you here, again, even if you're not following all the math, I can point you to the paper that walks through this. This sort of match right here tells me that if I want to find a branch back here, I need to sample X number of men in the present. If I want to find more branches back here, I need to sample Y, this number of branches in the present. The bigger point here is the matches we found so far give me a tool to know where to look in the world for in a more ancient branch and how many men to sample. Let me give you an example of this already working. So again, the paper in which I discussed this is here. Let me give you an example that's already working after I had worked out a conclusion, made some predictions, just to show you that this is already working and it makes even more predictions for the future. This is the type of math I'm using to try to find more ancient Middle Eastern samples, the lineage of the ancient Sumerians and the Assyrians and all sorts of stuff, ancient Mayans. If you watched episode 1, you know I talked about this particular branch of the tree known as haplogroup E1B1B, back to our big tree right here. It's this section right here. And you might recall that I talked about multiple lines of evidence pointing towards E1B1 being associated with the migrations and conquests of the Arab Muslims. You also know that we talked about it being linked to the E1B1A, a dominant sub-Saharan African lineage. The linkage between this, what I'm calling Arabian lineage, and the sub-Saharan African lineage is about the 700s to 400s BC. And to make a long story short, I argued that the ancestor to both of these groups existed in northeastern Africa in the distant past, and that they eventually went their separate ways in the 700s to 400s BC, one ending up this way, one ending up in the Arabian Peninsula, even though the origin was Africa, and pointed towards the kingdom of Aksum, which connected the Arabian Peninsula and what's basically now Ethiopia, Eritrea, in the first few centuries after Christ. Okay, why does that matter? It makes predictions about how many men you have to sample to find an ancient branch and where to go looking. Say what? Well, this is something I'd worked out by February of 2021 because I had already submitted a version of my book to the reviewers. They had gotten back to me and I was about ready to publish. Didn't have Noah yet, but had the history worked out. Well, September of that year, several months later, this paper gets published, A Genomic History of the Middle East, which includes Y chromosome data. You can go look at one of the later figures in the paper. You probably won't be able to read this, but I'll zoom in here in a moment, but you can see each of these men are labeled with a detailed version of E1B1B. All these men belong to the branch E1B1B. Okay, so what? Before this study, the deepest Y chromosome branches that were found went back to the 300s to 600s AD. Again, my model predicts as that you sample more and more men, you're going to discover more and more ancient branches in a very mathematically precise way, and they'll show up in spots that I predict. So back to the paper that they published, the tree that they published. I've advanced too fast here, my apologies. I'm going to draw a parallel here for you. These 3 branches right here, you can find on the tree right here. So if you go from this point forward, time moves from left to right, just like in my diagram. This is as much as we had known before this paper, yet they added a more ancient branch right here. They discovered a more ancient branch. First example of this that I knew of. These dates here are given in terms of evolutionary time, but the point is you can line up this structure with the structure I just showed you, and it's objective that this is now a more ancient branch, and they talk about it in the paper. It leads to a male from Yemen. Yemen is right here, exactly at the geographic point that I said these branches entered into the Arabian Peninsula from an African homeland. It's this sort of thing where I can say, okay, breathe a sigh of relief. This is working out the way I'm intended. I expect it to. I can't intend it. Discoveries happen independent of me. This is working out the way I predicted. So now let me summarize for you just this little section of Y chromosome history. Even if you didn't follow every single point, the larger point that I want you to see is that there is a chronology here. You can look it up for yourself in the publicly available data in terms of papers I've presented or talks I've given, papers I've published, several of them over time, and compare to what the book says now and see this progression, predictions, fulfillments. We started And again, the whole reason I've reviewed all this is to show you we've started with this father-son mutation rate. We didn't stop there. This predicts a match between the history of human population growth and a reconstruction from the Y chromosome tree. Didn't stop there either. This predicts regional matches, found those as well. Didn't stop there. Predicts that we should be able to find the history of civilization embedded in the Y chromosome tree. Didn't stop there. Kept predicting things. This predicts that we should find the Genesis 10 echo at the base of the tree, perhaps the most explosive confirmation of the biblical history. Didn't stop there. We continue to predict where and when on the tree branches should arise. And this model predicts branches should continually be discovered because of, again, even if you didn't follow the math, because of its match to this history of human population growth. It's continuing to work. And really, to step back, how do we know this is true? If it continues to work, we'll know it's true. That's just the way science works. How do we know the Y chromosome element is true? Because it's part of a historical progression of discoveries in which successive testable young Earth creation predictions keep working. That's the point. That's the standard that evolutionists have demanded. We have gotten to the weeds a little bit. We've actually skimmed the surface from another perspective because there's a lot we haven't said. And I hopefully you've seen the papers if you want to dig into the technical details. The bigger point is there's a lot behind what's going on in this book Traced. And there's even more. Just in the last few minutes here, I want to shift gears and say, let me back up this story to 2013. I said there's a decade-long series of experiments that have led to this. I started in the middle of the story because I wanted to tell the Y chromosome element of it, because that's at the heart of this book Traced, but that's not the only line of evidence. That's not the only chronological sequence of predictions and fulfillments that lead to this. In 2009, when I started in creation science professionally, the biggest data set that was available, or the one that was most readily accessible, was not the male inherited DNA of the Y chromosome. It was the female inherited DNA, the mitochondrial DNA. Both men and women have it, but as best we can tell, only moms pass it on. I have my mom's Y chromosome DNA. My children have my wife's. We'll talk about the DNA we get from both parents because it's part of the chronology as well in the next episode. But where all this started, again, shifting gears from the Y chromosome way back now to 2013, 2009, this is where I began the research. And at that time, part of the reason I started with this is because when I joined the Institute for Creation Research, the first task I was given from a research perspective was to come up with a research program. Long story short, when I'm tasked with stuff like that, my first job, I see, is to find the questions that need to be answered. So we came up with about 8 questions, all of them revolving around the origin of species in general, with the question of the origin of the human species as a particular subset of that. And the first paper then, major paper I published along these lines, looked at the mitochondrial DNA, so there's your mitochondrial in the title, from 2,700 metazoans, so multicellular animal species and humans. And most of this paper comes up with trying to derive a testable predictive model for the worms versus human differences, or the fruit flies versus mammal differences, whatever it is. Thousands of species. How can we make sense of this in a scientific way? Because no one had done this. That's most of the paper. But at the end of the paper, this is where we get our first links now to the Y chromosome data indirectly. I talked about 4 species, the only ones that I knew of, metazoans, in which the parent offspring mitochondrial DNA, female inherited DNA, mutation rate was measured. So at that time, it was published for roundworms, fruit flies, water fleas, and humans. If you know your animal classification, these roundworms, Caenorhabditis species, belong to the phylum Nematoda. I'll explain the significance in a moment. Fruit flies, Drosophila species, technical name, and water flea or Daphnia species, both belong to the phylum Arthropoda. Humans, having a backbone, are classified in the phylum Chordata. So 3 different phyla. So even though it's 4 species, it represents a very big swath of life. And they all gave the same answer. Again, you can look at the details in this paper. I did something similar as I did for the Y chromosome. This is where it began. Get parents, offspring, get mom's mitochondrial DNA sequence, get daughter's mitochondrial DNA sequence, compare them, count the number of differences. In this case, the mitochondrial DNA is not 10 million, 60 million letters long. It's only about 16, 17,000 in humans. And it's not that much different in these other species. And the rate of change, if you think about mutations per generation, at least in humans, is about one mutation every 5 to 10 generations. Point being, even if you don't follow the technical details, just as we saw for the Y chromosome, the mutation rate that was measured in multiple species was all very fast. And you probably can't see the details here, but you can see the general shape. And red is the evolutionary predictions. So you look at the evolutionary literature, these species supposedly originated 18 million years ago, 7 million years ago, 20 million years ago. In this paper, I said 180,000 years ago. For human origins, I had to correct that because we're looking at non-African data back to about 50,000 years, 100,000 years. The red bars represent the evolutionary expectations. If this fast rate is going fast for a long period of time, you're going to get way more mutations than the species can tolerate. Whereas the predicted number of mutations for the young Earth model in just 10, so I used the time frame of 10,000 years. Redid some of that in later papers down to 6,000 years, but there's an overlap. Even if you can't read these numbers, you can look up this paper again. The reference is here. Multiple independent lines of evidence pointed towards, and mitochondrial DNA pointed towards it being explicable in just 10,000 years. It was consistent across animal phyla. There was an explicit treatment of human origins, and this made predictions for the future. That's perhaps the most critical element of all this. Sure, there was a match, and we'll talk about next time some of the evolutionary responses to this and criticisms. But the gold standard of science is testable predictions, and I have put in print predictions about the rate of mitochondrial mutation for other species. And again, I don't decide what we get to predict. It's just what's left to discover. And this is one of the key things that's left to discover. I've put in print predictions for the mutation rates of the species. And just like we saw in the Y chromosome data, no one had measured or has measured the African mother-daughter mutation rate for humans, put predictions for that as well. So this is where it began. Again, I've finished the Y chromosome story that went back in time. And in our next episode, we're going to bring it all together so you can see one long progression over a decade of things that are connected. You can probably already see at this stage, even though we're talking about a different genetic compartment, a different type of inheritance, a different gender inheritance that we're measuring, mom's line of inheritance, maternal inheritance, we're seeing a similar sort of thing result. And it was the same pattern of results, predictions, fulfillments that eventually led up to this Y chromosome results that's contained in this book, Traced. How do we know it's true? Part of a historical progression of discoveries in which these predictions based on the young Earth keep working. You can find that book, again, for sale, multiple outlets, Amazon, Answers in Genesis. There's an audiobook. There's a Kindle version. In our next episode, you'll see the relevance of this book in particular. You don't have to have read this to understand Traced, but there is a prediction fulfillment connection between these two. The simpler version of this, the Cliff Notes version of this, is this book, Replacing Darwin Made Simple. If you want to participate in future research, we'll put this link here on the screen in a moment. You can go to answersingenesis.org/go/traced and scroll down. You can enter your name, email, message, because once again, we're testing predictions. The mathematical relationships that I just showed you are the basis for what we're doing going forward and will be the basis for quite some time. Hopefully you can see that we've been doing science for about a decade and we have no intentions of stopping anytime soon.
I love that phrase there at the end. We've been doing science for more than a decade and have no intentions of stopping anytime soon. And I know that to be very, very true, knowing Dr. Nathaniel Jeanson really well. So much good stuff, so much good science, good meat to chew on, to really give us a good backing for the stuff you've been talking about throughout your book. I will tell people that if they get their copy of the book Replacing Darwin, they really should check into that. This is my own copy, my own signed copy, by the way. But it's so powerful, both it and the book Traced, because what they both do, and I find this fascinating, and it makes sense within the biblical worldview, that as we look at science, rightly understood, it confirms the Bible again and again. So what we expect to see, we do see within the biblical framework. We find that in the actual data. That's a great confirmation of the biblical worldview. But then on top of that, you're not stopping there. We're not stopping there. We're going to make predictions because we expect in the future we'll have more findings that again confirm that biblical perspective, because God's word is right about everything. And so you have that confirmation of what we already know, things lining up. That's wonderful. and then predictions set forth in the future to see these confirmed again and again. And I can't wait to see it. I'm so excited about that. So excited about the future research that we're doing here. So, guys, I know you want to keep up with this. Keep following along. Follow Dr. Nathaniel Jeanson on his different social media pages. Follow the Ministry of Answers in Genesis, our website, answersingenesis.org. Get the resources, devour those, share those. Such a needed message because, again, the point of doing all this, we love doing science. We love science here in the ministry. We really, really do. But the point of doing good science is to proclaim the glory of God and share the truth of his word and proclaim the gospel ultimately. And so that's really the heartbeat behind all of this. And so get involved, get in contact with Dr. Jeanson if you'll be involved in the research, and be sure you stay tuned for the next episode coming up, and we will see you then. You guys have a good day. God bless.